Throughout this video, I'm going to describe how for my remote sensing semester project, I turned the Jim Henson statue on the left into the 3D point cloud on the right. Various skills and topics were covered over the course of the semester. Masking images using thresholding and detecting colors and changes in pixels were demonstrated through both lane detection and Ring doorbell assignments. Understanding the Raspberry Pi system, its camera, and how it interacts with your computer is introduced through taking pictures through Python. Color masking with upper and lower bounds was introduced through stoplight tracking. Pixel manipulation was introduced through applying a noise to an image and then filtering this noise out. Finally, the LiDAR equation and how it works with LiDAR sensing was covered. All of these topics were combined to create a 3D point cloud of an object on campus. For my project specifically, I chose the Jim Henson statue in front of Stamp for various reasons. One, it is a popular statue and involves Kermit, and who doesn't love Kermit? Additionally, the statue has various complex features that present unique challenges, but also help me demonstrate the full advantages of LiDAR sensing, which are enhanced resolution and precision when creating a 3D shape. The design of my sensor included the basic features of a LiDAR sensor. The transmitter was represented by a LED line laser, glued in place and powered by an Arduino. The receiver is represented by a Raspberry Pi camera, zip-tied in an upright position so its lens is aligned with the laser. Finally, the system control and data acquisition are completed by the Raspberry Pi, with data analysis later completed by myself. The laser and camera are held at a known distance of 12 inches from each other, which is important for later calculations. As seen by the diagram to the left, the laser emits a beam which spreads out in all directions. One of these directions is aligned with the lens of the camera, which the beam crosses and eventually lands on the focal plane of the camera. The further away this beam is from the LiDAR rig, the less pixels from center it is from the center of the focal plane, as seen by the graph in the top right. This is due to the equation in the bottom right, which includes d, the distance to the target, h, the distance between the transmitter and receiver, which is at a known distance of 12 inches as noted previously, the PFC, which is represented by the pixels from center, RPC, the radians per pixel pitch, and RPO, an offset value. RPC and RPO are later adjusted through calibration of this LiDAR sensing rig. A demonstration of this can be seen by the image to the right. The backrest of the bench, further away from the camera, is less pixels from center than the bottom of the bench, which is closer to the camera. Calibration process, I ensured that the laser and camera axis were aligned and parallel using this Python script here in the setup. And after making sure they were aligned in parallel, I then taped and glued in the laser to my rig. And once this was completed, I then took distance measurements from my wall, moving it back 6 inches at a time to calibrate the distance of my LiDAR rig, and this led to these JPEG files seen here. As you can see, as it moves further away, the line gets closer to the center. And after this, I used these to come up with this RO and RPC value seen here using this calibration curve, and using theoretical distances, I aligned all of my measurements to this curve by adjusting the RO and RPC value. So the next part in this process was, after calibrating the actual LiDAR sensor, was then setting up the rig and beginning the deployment process. And so this can be seen here. It involves actually setting up the tripod and then screwing in the tripod attachment to the LiDAR rig, and then screwing in the tripod attachment to the tripod itself. And one thing to note about my setup is that I have my laser above the camera, as this was the most adequate for me recording images and eliminating noise. And then I actually brought this setup out to my target itself, with the only difference here being the Bubble app on the phone recording angles, as well as a portable battery pack to power everything. And so I took eight measurements, the first 4 here, and then the next 4 here, and these were all 8 scans that I took using the positions of the tripod as seen here. So I really wanted to focus on getting close up, small field of view scans, in order to get a lot of detail in my recording. And then as you can see here, here's how the actual scanning process plays out. And it just involves moving it up 2 degrees at a time using the bubble level app on my phone. And so basically the X field, the X coordinate is fulfilled by the actual horizontal laser line, the Y being the distance to target using the fundamentals of LiDAR sensing, and then the Z using the bubble app on the phone, knowing what angle you are actually taking your recording at. My deployment process, as seen in some of these images that I hand selected, there was some noise in the background, whether it be due to the lighting in the street or objects in the street or the lighting on stamp as well as the brick wall of stamp. So the first way that I eliminated this noise was making my laser line much more defined by basically twisting its head to calibrate it to get me a much more thin, intense laser line that was easier to see. Another thing I did was place the Raspberry Pi camera below the laser line, so that way it was closer to the ground and the statue kind of provided a little bit of shadow and helped get rid of some of the glare faced by the lighting. Another thing I did was use a color picker Python script to essentially adjust hue saturation values for each image of each scan and figure out what worked best for each scan. And then I applied this knowledge to Python using a different color and lower bounds for most of my scans. So here you can see I use a certain color lower and color upper range. And then for this one, if the angle was within a certain range, I wanted to use a different color mask and then use a mask to black out some of the image and get rid of noise. And then if it's outside of this range, I want to use a different color and color lower and color upper value. And so I did this for all 8 of my scans, just figuring out what worked best. And then this created a 3D mesh in Python. This is just showing one of my scans of the Kermit close-up. But as you can see here, there's still some noise. So then I loaded these text files into MATLAB and translated and rotated these point clouds through adding or subtracting values to each column or flipping columns and applying negative signs. And then I got rid of noise by using this MATLAB functionality, basically saying if there's any outliers within each scan, I want to basically amount them to nothing and get rid of them in the array. I used a special rotation for the Kermit close-up with a last minute change here and to help it mesh with the rest of the points. So then I used PC Show to essentially show how these all came together. So here's all 8 scans before I put them together. And then after I meshed them all together through translations and rotations, this is what I got here. And you can see a lot of the key features in this scan. You can see Jim Henson's legs right here. You can see his arm right here. You also get a little bit of Kermit's legs right here. You can see Kermit's arms in his head. So I was able to get a lot of the unique features of the scan, and overall I was pretty satisfied with it. The final thing that I did was put it into MeshLab, apply a normal filter and a surface reconstruction, and then delete some of the surface. And overall, because of my scan was so detailed and complex, MeshLab struggled with it, but you can see the general features of the scan.